So yesterday we talked about the things that affect the rate. Let's talk about the actual rate law itself today. It is a mathematical expression that relates the concentration of reactants to the rate. And remember, yesterday we talked about when we're measuring rate, we're either going to be measuring the disappearance of the reactants or the appearance of the products, depending on whichever one is easiest to observe. So the first thing is that the rate law is found experimentally. And is based on the slowest step in the reaction mechanism. And we're going to talk about the reaction mechanism in a second. It's always based on the slowest step. Okay? So kind of like the chain is only as strong as its weakest link, a reaction is only as fast as its slowest step. Okay? So let's talk about the reaction mechanism before we try to calculate rate law. Okay? So what we've been seeing so far when we see a balanced equation is we've actually only been seeing the net overall change of what's going on. Okay? Kind of like if I wanted to go from here to Dallas, my overall mechanism, my overall reaction would be Houston to Dallas. Okay? But there's a lot of different ways I could get there. I could go 45 if I want to go really fast, or if there's a traffic jam, I can take some side tours. Or let's say I want to stop in Temple and see my mother, or I want to go to Magnolia Farms. There's all these different ways. Those would be the reaction mechanism, but my overall net change is I started in Houston and I ended in Dallas. Okay, so that's kind of like what we're doing with the reaction mechanisms for equations. We've just been seeing the overall net change. Okay, we start with these reactants, we end with these products. Okay. And yesterday we kind of talked about the activated complex where it's changing, and they talked about in the video there's different things. That is kind of like that. We're going to see something called intermediates. They're not the same as the activated complex, but it's a similar concept. Okay? So let's look at this pretend reaction. And the overall, so under yours, draw a line, and the A to D would be the overall net reaction. So that's what we would start with, and that's what we would ultimately end with. But in order to get there, we had to go through a series of these steps, and these are the steps in the mechanism. I'm going to run out of room, sorry. Okay? So A would go to B, then B goes to C, and then C goes to D. So just like when we were doing redox and we canceled things out that ended up on the opposite sides, we would cross out B and we would cross out C. And those things are called intermediates. And what intermediates are, they are things that are created and then subsequently used up in a later step. Okay, so they do not appear in the overall equation. But without them, we couldn't get from A to D. Okay, they have to be created, but then they're used up. Okay, so here is a real example of a reaction mechanism without using letters that we don't know what they mean. So this is the formation of hydrogen iodide by iodine and hydrogen. Okay, and so you can see that this should also be marked out right here. Okay, that I got left out. So I2 has to break apart into two iodide separate. Then that reacts with hydrogen, and we get this H2I. And then the H2I reacts with another iodine, and that's how we get this final thing. So in this case, 2I and H2I would be your intermediates. Okay? Because they are created and then used up in subsequent steps. So our final net would be this one right here. So this would be your overall net. Because if we were to put this in a container, we wouldn't see evidence quite of these middle steps, but they have to happen in order to get the final product. So they're called intermediates because they're created and they immediately react. Let's say that this was the slowest step, then that would determine how quickly this reaction, because this step might take a long time, but then the third step might happen really quickly. But that's determined experimentally. Okay? For this, you have to understand what a reaction mechanism is, the steps and the intermediates, and that the final one is the overall net change. Because when we're going to do rate laws, we're going to do as single step, which don't have a reaction mechanism. They just are single step. So that's the only thing we're going to determine rate law for. Okay? Any questions so far? It's one of the reactants. It's like I would add, if I added iodine and hydrogen together in a flask, ultimately they would create hydrogen iodide. Okay? These are steps along the way. So what has to happen first before anything, even though they're all in there together, the iodine first has to break apart. Okay? Then once it breaks apart, it acts with one of the hydrogens that we put in there, and it forms this H2I. Then one of the H2Is reacts with an additional iodine, and then we get the HI. Okay? So these are the steps in the process. Okay? But ultimately, I added these two in there to make it react. But before it made hydrogen iodide, it had to go through these processes. Okay? So there can be more than one reaction pathway. This is the way we showed this. There are some other ones that could happen, maybe not for this particular reaction, but there are some reactions that can get there a couple of different ways depending on what parameters or conditions they're in. Okay? But remember, the things that appear in one step and then disappear immediately and they don't end up in the final equation, those are your intermediates. Okay? So let's talk about single step reactions. That means the reaction mechanism is just the one step. Okay? So for this particular equation, we have the rate for this would be the reactants raised to their coefficients. Okay? So these are like if this were coefficients of 1 or 2. Whoops, sorry. I forgot to hit that I was going to write. So these are the coefficients in the balanced equation. So the rate is going to be the concentration, because remember brackets is concentration, of your reactants raised to their coefficients. And that's going to be what your rate is equal to. Okay? And then K is our specific rate constant that we can calculate for.
Wait, so what are A and B again?
Your reactants. Yeah. Your products do not appear in the rates law that we're doing. Your products don't appear. Okay? So the exponent of each reactant's concentration is called its order. Okay? And the sum of all the exponents is called the order of the overall reaction. And so we'll show you an example. So in this particular equation, this is how I would write the rate law, right here, because there's just 1 and 1. So and this is the way you would say it. It would be first order with respect to NO2 and CO, and second order overall. And all I did was add up the exponents. 1 plus 1 is 2. Okay? Let's say I had this equation.
Wait. So you don't like do anything with that? You just say rate equals K?
Rate equals K times the concentration of nitrogen dioxide and CO, because there's only ones. But if you looked at this one, we would write this as rate. Hold on, I need to see. I need my lab manager to set up for y'all's lab tomorrow. Okay, so this would be rate is equal to K, and then we would say H2 squared, and then O2. So it would be second order for hydrogen, first order for oxygen, and then what would it be overall? Third order overall.
You have time out there.
Okay, your exponents. Okay, your
Yeah, I see what you're
exponents.
talking about.
Okay, because we said that on the last slide. The exponents, first order, second order, third order, is what you're raising it to. Okay, so the fact that this had a 2 here, we had to do concentration raised to its coefficient. So it would be second order, and then since there's not one there, it'd be first order for oxygen, and then for the overall reaction, you just add up the exponents. So it's third order overall. Do you want me to do another one?
Can you leave one there?
Yes, I can do another one.
Because, so the hydrogen has a second order and the oxygen is at the first order, but you don't put a 1 there, it's just a third, so 2 plus
Yeah, you don't, if you're raising something to the first power, you don't put it.
Wait, so you don't add?
Yeah.
Kind of like what you said?
Degree in math.
Kind of. And so in this particular reaction, if I were to look at this, if I raised the concentration of hydrogen, it would have a higher effect on this equation or this rate than if I raised the concentration of oxygen. Do you understand that?
No, not the same effect.
No, it wouldn't, because I'm squaring hydrogen's concentration. So it would change the rate more than oxygen would. Let's say I doubled the concentration of both reactants. Hydrogen's doubling would have a greater effect because I have to square its concentration.
Yeah, but if you just doubled oxygen, it'd be 2, and then they'd both be 2.
But if I doubled both of them, hydrogen would affect the rate more.
So you're saying, yeah. So you're saying you'd have to do them together.
I'm just saying, if I were to ask you a question, if I doubled the rate, if I doubled the rate of both, which would have a higher effect on the
If
rate?
it's both, then yeah.
I said both.
Okay, well, first you just said changing the concentration of hydrogen has
Would-
a higher effect than oxygen.
It would. It would have a
If you
double.
just change oxygen on its own, then it wouldn't matter.
Okay.
No, I see what you're saying now, but the first way you worded it, you made it sound like you could do it to each one individually.
No, I'm just
In
saying.
that sense.
I'm saying in this particular reaction, hydrogen's concentration has more effect. It affects the rate more than oxygen's does
Is that because
by
there's
changing
that-
it because there's a 2 because it's squared.
Okay.
Okay. Yes. So let me do another one since some of us are, okay? So let's do, let's balance this, practice balancing from the good old days. Okay, I'm going to need to do that, right?
Oh, so you do the orders after you balance?
Yeah, it has to be balanced. Absolutely has to be balanced. So that's 8 plus 6, 14, so that's 7, right? Did I balance it right? I did that very quickly. Now, you would never, in rate laws, you're not going to see one. This would not be a single step in a rate law, but we're just going to do it as if it is. Okay? So our rate would be K times C2H6 raised to the second times oxygen raised to the 7th.
O2.
Oh, sorry. Now, like I said, in rate laws, you would never see one this high. It was the first example that popped into my head. So in second order for C2H6, 7th order, which you would not see for O2, probably should use a smaller example, and then 9th order overall.
Okay. I get it now.
Yeah. Again, let me caution you that you would never see a rate law with that high of an exponent, okay? Because it wouldn't be a single step, and whenever it gets that high, there would be a mechanism, and then there's a whole another way that you look at it that way. We're not going to do that in here. We're only doing rate laws for single steps.
Single step means
One step. There's no mechanism. It's just one step, okay?
It's just straight bam bam.
Straight, yeah. And there are some single step, obviously. Okay, so let's do some calculations. Okay? All right, it says this particular problem is wanting us to calculate for the rate constant when we know that our concentration of A and B are both 0.2 molar and that it's giving us the rate. So it's already given us the rate. So we want to write rate is equal to K times the concentration of A times the concentration of B squared because of that 2. So it gave us a rate of 2.0 times 10 to the negative 4 equals K times 0.2 molar times 0.2 molar squared. Okay, so if this is our rate law, we're going to solve for K. So then it's just basic algebra. Here's the tricky part, and this is what would trip you up. This is what would trip you up on a test, because it's not very hard math, But you got to pay attention to your units, because figuring out what the units are for K is the difficult part, and that gets them even in AP Chem. Okay, so here's what I suggest. Let's write it all out. Let's do our math, and then let's go figure out our units last. Works better that way. Okay, so we're going to solve for K. So we're going to have 2.0 times 10 to the negative 4 molarity per second divided by 0.20 molar, right? Times 0.2 squared molar squared. Okay? So someone has calculators, I hope. So it's going to be 2.5 times 10 to the negative 2. So now let's figure out our units. Okay? Up here we have meters per second. Okay? Down here we have meters times meters squared, not meters, molar. I don't know where meters came from. Molar. Okay? So this is molar cubed.
I did not get that.
You didn't get m times m squared?
No, I got 4 times 10 to the negative 5.
Did you remember to square the second point 2?
Yes.
Did you use some parentheses, because that makes a difference?
I did.
Because this is the answer. Okay? Now, so look here. This is excuse me, gentlemen and ladies. Don't make me call out your name. Okay? Let's talk about units, because that's where, like on the AP exam, if you were to do this, it's let's say 1 point for the answer, but it's a whole point for the units, because the units trip people up. So well, let's talk about it in a minute. Let me go through this first, okay? This molarity would cancel out, and what would that leave you with on the bottom?
M squared.
M squared. So you can write it like this, m squared times second on the bottom, but oftentimes the way you will see it is you will actually see it like this. M to the minus 2, S to the minus 1. So that they don't have to do that slash. That just means it's supposed to be on the bottom. Okay? So you can show it like this and put it on the bottom, or you can do the M to the minus 2. Occasionally, you might even see it as liters over moles times second. So sometimes, because if I upside down a molarity, I get this as well. So occasionally, you might even see it like that. That would have been squared for both of those, though. So there's different ways to recognize it. But the units kind of get people, because they forget, they square all the numbers and they forget that, hey, I got a unit attached to that, I got to do that. Okay? And in terms of A, what order do we have? In terms of A, what's our order, May? May, what's our order for A?
I wouldn't know even if I was paying attention.
Okay. Pat, what's our overall order?
3.
Third order overall. Okay? Third order overall. First order for A, second order for B, third order overall. Okay? Now, the next one is going to ask us to calculate K, not K, rate if we change the concentration. So now that we have K, it's a rate constant. So we know that that K value is the same for every parameters we could put in there, because it is a rate constant for this particular reaction. So on the next one, if I was to change my concentration to 0.3 molar, what would that do to the rate of reaction? Okay? So same rate law as what we had. Rate is equal to K times A B squared. Okay? This time we're going to be solving for the new rate, because we're at different concentrations. So we're going to use the K value that we just calculated. And then we're going to put in 0.3 molar. And then we're going to put in 0.3 molar squared. And then we're going to calculate that. This we got from the previous problem, because once we know the value for K, it's the same no matter what our concentrations are.
That's an F.
That's an S, it's a unit, yeah. Okay, so now when we plug all that in, we should get 6.8 times 10 to the negative 4th, And now what would our units be?
So this is 2 sig figs.
Yeah, molarity per second.
Just in.
Molarity per second. Because now these two would cancel out these two, and then that second's on the bottom. So that should be our rate. Okay, so that would be our new rate at that concentration. Of course, we could put the concentration at 0.5 molar, and we would use that same rate constant, K. Okay? So the math is pretty straightforward. You just got to pay attention to your units.
Where's little -1 on the S bill?
It's telling you that it's per second. But whenever I don't have a unit on top, I don't like to just write /s, so I do the negative. Whenever you see a unit raised to a negative exponent, it means it's supposed to be on the bottom. Yeah. Yes?
Can the rate ever have like m squared over s, or will it always be like m over s?
Oh, yeah. I mean, if one of those had been third order, then it would be on the bottom. Or if it, if it had two orders or whatever. It depends on, and honestly, in AP Chem, you get to where you recognize the order based on what it is. But then there are some rate laws where only one of the reactants actually appears in the rate law. So, but we're not probably gonna see that in here. But in AP Chem, yeah, you can also have zero orders. They're not very often, but you can have zero orders where rate is just equal to K. Yeah. Okay. Okay. So add these definitions to your notes, and then that's where we're done. So add these in because that one got left out of your notes.
Where